So, Sherry gave us a lot of information earlier on about aquifers. What we want to do, the purpose of this little session, is to pull out what is the essential understanding that we would want kids to have about aquifers, that they would take away from the edible aquifer activity that you guys did before. So Mary and I, Mary's a water quality specialist at the Iowa Department of Natural Resources Geological Survey. We're going to talk about, and this is the same slide that Sherry had before, what is an aquifer system? And then you're going to be thinking about how does that relate to what we did to building the aquifer in the little glass cup that we did before. So, Mary and I are like, what you talking about? So basically, here's how an aquifer works. This is a cross-section through the earth, okay? And in that cross-section of the earth, you have rocks down below, layers of rocks down below, and then you have, on top of those layers of rocks sometimes, unconsolidated loose materials like sand and gravel. And what happens is water rains down on the earth, and it goes down through these different layers, and it ends up in certain layers, and those layers become aquifers. And now what makes a layer of rock or unconsolidated loose materials an aquifer is that, and Sherry had this before, that you have to have what's called porosity. And that is space between the grains that make up the rock. And then the water goes in and fills up those spaces. And the second thing you have to have is permeability. And permeability is the connection between the spaces. So not only does water go down and fill the spaces, but it can move between the spaces so that when you drill a well down in it, you can pump the water out. If the water was stuck in the spaces, you wouldn't be able to pour it out. And so basically what happens is the water goes down and it finds a layer that has porosity and permeability. In this case, it's loose sand and gravel here. And the reason why the water stays in there is because beneath that layer, you have another layer that is, and Sherry said the word before, it's impermeable. So permeable means you've got spaces that are connected that water can flow through. Impermeable means it's almost like a layer that water can't move through.
It's a barrier.
A barrier, that's the word I was looking
for. So it's like a cap that sits on top of your aquifer that prevents contamination or just water from getting in there as well.
So the water went down through here, it found this porous permeable layer, and then this shale below it, which is impermeable, kind of acted as a barrier and stopped the water from going any further. Or it maybe did go a little further, but it went very, very slowly. Now down here there's another aquifer, and in this case it's a limestone, and the limestone doesn't have spaces between the grains. And Iowa's full of limestone. But what it does have is fracture systems. And those fracture systems can fill up with water, and you can then drill into the fracture systems and pump the water out of the fracture systems. One of the big misconceptions that kids have, that a lot of people have about aquifers and how you get water out of the ground, is that there are vast lakes under the ground, or rivers under the ground. And the water is flowing through the rivers, or flowing into these lakes underground, you can pump the water out of the lakes. That doesn't happen. The only place that it happens once in a while is maybe down in Florida, where you have what's called
karst, caverns, and that kind of thing.
Caverns.
So the limestone, so part of what John's getting at that I think is really important, that is a learning take-home message, is that you get this secondary porosity that forms in limestones through fractures. And then as the water moves along those fractures, it dissolves that limestone. And so you end up with spaces between them. But that's a secondary porosity, not an initial porosity that occurs in that rock like a sandstone might have or something that's gravel have. So that's an important piece for the kids to, I think, look at, is whether it's secondary porosity or initial primary porosity that's in that, inherent in that material. The igneous rocks have the same thing. You may get fractures and water moves down to that fracture. Essentially, this is very permeable naturally when it's first formed, but you will get secondary porosity in there through tectonic activity or something that's just breaking that rock up.
Yeah, let me say that this is kind of like just one simplified diagram of what a system might look like, but there's all kinds of variations on this. Like for instance, we have the igneous and metamorphic rocks at the bottom here. We call that the basement. And in Iowa, this is kind of what happens. And the basement is down like 30,000 feet in some places in Iowa. But in Colorado, where we lived before we moved to Iowa, The basement, this big metamorphic rock, was right at the surface. And we built our house right on the metamorphic rock at the surface, and we had to drill a well into metamorphic rock, and that's not an aquifer. So we had to hope that there were fracture systems down here somewhere that were holding water, and it was like, $20 a foot to drill it. We drilled it 600 feet and still hadn't had water. And so we were waiting to hit those fractures. So the bottom line is that this is just one generalized sort of schematic of what an aquifer system could look like. Here I've got loose sand and gravel, and then the shale below it. But this could be a sandstone, not loose sand and gravel at all, but an actual hard rock sandstone. And the sandstone still has little spaces in between the sand grains, and the sandstone could be bedrock, but it could still be an aquifer too, because the water is in the little spaces in the sandstone.
Yeah, and you may end up with limestone above the shale as well. So depending on the depositional environment, you may have limestone shale, limestone shale, limestone shale, and that with each successive layer of shale, you get more and more protection for the water below. So the shale is essentially, if it's absent, and there are places in Iowa where it is absent, anything from the surface that's moving down to the water, oil and grease, pesticides, I mean, they're going to move through, that shale layer is missing. But don't get locked into that. It has to be just a few layers. It may be 50 different layers of rock, depending on what's happened in the history of that location.
So here's the takeaway. The learning goals for this thing would be that, okay, down below us, in most cases, especially in Iowa, is layers of earth materials, some of which are rocks, and some which are unconsolidated materials. That's one takeaway you'd like to have the kids learn. That some of the materials are porous and permeable and hold water, and some of the materials are not permeable, they're impermeable, and they act as barriers.
The other thing that we didn't talk about, I mean, I don't know to bring it up, but so sometimes the water in this limestone aquifer may not have come from directly above here. This may have been originating 1,000 miles away, and that water slowly moving down that limestone aquifer, and the recharge area is way over here. So when you think about the quality of that water, it's had to go through either a lot of rock or it's had to come from a long distance. And that these confined layers are oftentimes legacy water, and essentially you're mining the water here. So you've all heard of the Ogallala Aquifer. That recharge is so slow as to basically not be recharged. And so that water gets mined because it's confined. Water can't get into it from above, and so it really takes a long time for any new water to get in there, and we're essentially mining that. And so that confined layer tends to be, oftentimes that those confined aquifers, you're mining that water, as opposed to seeing a lot of recharge that you might have in an unconsolidated, non-confined sand and gravel aquifer.
And the further the water goes down through here, or the further the water comes from, like in Iowa, down below us here, there's something called the Jordan Aquifer, and that Jordan Aquifer, the water can go straight down from here. If it rains here, it goes down there. But most of all, the Jordan Aquifer tilts all the way up, and it comes up to the surface in Wisconsin. And so what happens is the rain in Wisconsin rains on the Jordan Aquifer, and then works its all the way down, all the way down, all the way down, until it gets to underneath Des Moines here, and then we can pump it up from here. And that long journey that it took to get all the way from Wisconsin to here, that cleans all the pollutants out of the water. Because the pollutants stick to the little grain and lets the water go through. So what we'd like to do now is, what you're going to do is you're going to evaluate the activity for the learning goals that we talked about here. So before we go to that, though, I want to ask if you guys have any questions about how this thing works before you then apply your understanding. And albeit this is a complicated topic, you can take a whole course in college on it. We're just doing it in 5 minutes here. But if you have any questions, we'll answer them before we then apply that to the activity.
Explain to me then, you hear a lot about buffer strips and protecting the water, and that's all surface. So how exactly does that work? Is that just another filtering layer to go to the aquifer?
Well, here is a river here. That's a cross section. There's a river in here. So having a buffer strip here would prevent the pollutants from going directly into the river, and then that would go to the next river, like the Mississippi. But also, one of the things that's really important and interesting, it's good that you brought this up, is that this river is actually connected to the aquifer. The aquifer comes up right to that river level. So the stuff that goes into the river not only goes downstream, but it also goes out into the aquifer. So if you have this well over here, say if you had a well right here, the stuff that went into the river goes into the aquifer and back up the well, you'd be drinking it. So that's why they're talking about that. Good question, thank you.
Mine is a little different. How was the choice made, or on what basis was the choice made to teach this piece of material to us?
Well, you're going to use the DOS tool to evaluate whether or not the activity had the learning goals that we just talked about, or any learning goal, whatever the learning goals were. You're going to evaluate the activity for learning goals. So for us to do this today is helping you see what the science is, so you can evaluate it for the learning goals.
But I'm wondering, are you asking a different question?
Oh, I'm sorry.
We chose.
That's a partial
It,
answer, which is
it
good.
often takes several people to hear the question. So we chose this particular activity because the hygienics lab, this is one that's very popular with the lab, and you guys told me who designed this activity?
So we didn't design this activity, we actually got it from another source. And what's interesting about that, that really was an aha moment for us, many of our activities we do have experts on site, we know the background, the history, and this is one where we didn't have an expert on site so much. So as we started looking at this, we're like, well, this is an opportunity for us to refine this activity. And then we reached out to John, who's an expert, and Lynette, who are experts. And then we're looking at this as an opportunity to really, for many different ways, not just this tool, but also to really, we realized, wow, you should always have an expert look at any activity, because sometimes you're developing them and sometimes you're getting them from another resource. And even though it's a credible resource, like ours was a very credible resource, you may, because we started looking at it and knew that there were things that we needed to refine, even bringing it today.
That's exactly the question.
And
Okay,
how many of you go online to get activity ideas? I mean, doesn't everybody do that? So this says to us, we want to take a closer look, especially now that we have this tool.
The other thing is, I think, you know, water is in the news, and so I think you'll get to the, you talked about the relevance piece, but the Jordan Aquifer just had rules passed about the amount that people can withdraw. So that stuff is in the news right now, the quality of the water is in, so I think that there's a lot of timeliness for kids to grab onto, that maybe they're hearing about this, or if we go into drought, that we've got to ration water. Well, why do you need to ration water? And especially for those folks that are sitting here, we often think about this as being almost like a checking account of your water resource. So if you start spending that faster, you can end up in big trouble.
Run out of money.
You run out of money, and so you have to be really careful with those resources. But this is oftentimes where the big water suppliers go to first, because they can get a lot of water out of surface water. But you know, that permeability notion becomes really important, because if you start sucking on that aquifer really hard, it gets to the point where you can't get enough water to those entities, those communities. And so there's all these inherent problems that kids can really latch onto in terms of, you know, you don't have unlimited resources. So where are you going to go if you had to come up with a mythical new town? What's your best source of water based on how much you have to pump and the quality of that water, and on and on and on.
And one other part to that is from the state, we're the Iowa's Environmental Public Health Laboratory, and so we're looking at protecting Iowa's water quality, and we are doing a lot of testing for pollutants that are going into the water and stuff, so this is very applicable to laboratory science that we do. We may not be the expert on the aquifers or whatever, however, we're doing a lot of the testing, and so we do have scientists that are experts on water quality. So it's a partnership, which most of these things are, and it's very applicable to what we're wanting our future workforce to learn about, and it's so important for protecting the environment. We know that.
Okay. Any more questions before we?
Yeah, can I ask you an important one? What are your recommendations for translating this to programs that might not have a lot of planning time or experts on hand? I hear a lot of very technical terms, and
But you can make it non-technical, and
yeah, please give an example of how you might do that
here's one example.
to make it useful and beneficial.
So one thing you can do, and John and I have been talking about this, and I'm probably jumping the gun, But you could take a piece of sandstone, a piece of limestone, and sand, you could have the kids pour water on it. And you're gonna see that the water doesn't go into limestone. It's gonna go around it. So right away you think, well, how can that be an aquifer if the water goes around it? But then you put 6 chunks of limestone together, you see where the water is going. And so you can, porosity and permeability are difficult terms, but you can talk about cracks and spaces and void, whatever word works for them, and have them just play with those rock mixes. Pretty easy.
Well, I see a lot of potential for vocabulary words too, for those that are interested in literacy. So I wouldn't shy away from the
No,
big
and
words.
I do think though, because this is complex, and what John and Mary have shared is for our adult level. I'm wondering if, instead of starting at the beginning, it'd be nice to start in the middle, under activity engagement with purposeful activities. And instead of us deciding at our own tables what our learning goals are, to ask John and Mary to help us establish learning goals. Do you guys like that idea, or do you want to do it at your own table? Like, would you, how many people deal with kids through age 3 through 6? And how many K through 2? And how many preschool? So we got the whole, and anybody over 6th grade, anybody do junior high, high school. So we've got everything.
Well, and here's the issue with this thing too. I think that Sherry said this is a 4th through 6th grade activity. For little teeny kids to think of what's going on under the ground that they can't see, this might not be cognitively appropriate for them, because they have to imagine what's down below. But I think I know we got a spectrum of age groups represented here, so maybe we should just focus on what the grade level is. Does that work for you?
4 through 6?
4 through 6, and what would be the appropriate learning goals for the 4th through 6th graders that the activity was intended for?
Okay, so let's do that, knowing that we'll get the skills to take this home and try something on our own. So let's everybody work in their small groups, work through your activity guide, but I would recommend starting with purposeful activities under activity engagement.